Okay, guys, moving on to chapter 4. Chapter 4, we're going to review polynomial and rational functions. Remember that polynomial functions are any function that you can write with positive exponents that doesn't have x's in the denominator. Their domain is all real numbers. They make smooth curves, okay? So here are a few examples of these functions. A constant function is a polynomial function with degree 0 because it's just like the number like y equals 3. It has no x in it. A linear function is degree 1 because it has an exponent of 1, like a line. So that's like y equals mx plus b. Quadratics, we talk about those a lot. That's when you have like x squared, right? Anything that has x squared in it, that's degree 2. Notice a cubic function, they don't all look like this, but this is an example of a cubic function. A quartic function is degree 4. A quintic function is degree 5. Notice the higher the degrees get, the more curves maybe that they have, the more ups and downs that they have. There's connections that we can make with the degree and what we know about the graph, okay? So it says, what do you notice about even degree functions? What about odd degree functions? Well, if I double page this, even degree functions, maybe you notice if it's an even degree, like 2 or 4, maybe you notice the arrows go in the same direction. So arrows either go up like this or down like this. If you look at the odd numbers like 1 and 3 and 5, look at the arrows on those. They always go in opposite directions, so odd functions go like this, or it could go up on this side and down on this side. Other things to notice is that an odd degree function will always have an odd number of real zeros. So look on the odd one, like a degree 1 crosses 1 time, degree 3, degree 5. It could be less than that, but at least be odd. And an even degree function will always have an even number of zeros, okay? So knowing whether your function is even and odd tells you a lot about the graph. So we can talk about the end behavior, okay? So the end behavior is what happens as x gets really, really big and really, really small. And this is some bad formatting on my part because this is supposed to say leading coefficient negative right here. Like this is supposed to say negative, but it went down to this, but I didn't notice it and I'd already printed it, okay? And the same thing with this. This one says leading coefficient positive, and this one's supposed to say leading coefficient negative, so you got to fix that. This is like a little chart, and if you had me for Algebra 2, then maybe you remember this little chart or the way the arrows go. And so leading coefficient and the degree. If you know that, you can tell me how the arrows are going to go. So if your degree is even, which means the highest exponent is an even number, when the leading coefficient is positive, the arrows are going to always both point up, like y equals x squared. Both arrows point up. But if I ask you to describe the end behavior, you're going to write it like this, okay? You're going to say as x goes to infinity, that means as x gets really, really big, what's happening to y? Well, we like to say f of x instead of y. Well, f of x is also getting really big. It's going up like this, so that would be going to infinity. And what happens as x gets really, really small? Well, as x goes to negative infinity, f of x, which is the y, it's still going up on this side, right? So it's still going to positive infinity. So we say as x gets really big, what's happening to y? As x gets really small, what's happening to y? So if it's even and the leading coefficient is negative, that would be like negative x squared. And if you think about the graph of negative x squared, both arrows point down, and that will be true for any even degree function. So again, this part's going to stay the same every time. You're always going to say, as x gets really big, what happens to y? As x goes to infinity, f of x goes to what? And as x goes to negative infinity, f of x goes to what? Well, since they both point down, we're going to say negative infinity on both of these. So notice on even functions, the y values always point in the same direction. They both point up, they both point down. Now, if it's an odd degree function, the arrows are always going to go in different directions. So if it's an odd degree function and the leading coefficient is positive, that's like y equals x cubed. And if you graph that, if you graph y equals x cubed, the positive side goes up and the negative side goes down. For every odd degree function with a positive leading coefficient, that side, that's going to work like that. So I always do the positive side first. Some people like to do the negative side first, but I always write it like this. So again, these parts are never going to change. It's just what's happening with y that changes each time. So I'm going to switch colors again. So this is saying as x gets really big, so the right side of my graph, as x gets really big, what's happening to the y? Well, it's going up forever. So it's going up to infinity. But as x gets really small, that would be the left side of my graph. The y's are going down. So notice they're different on this one because the arrows go in opposite directions. But I always remember if the leading coefficient's positive, positive stays positive, negative stays negative. Okay. So the last one, if it's odd with a negative leading coefficient, that would be like negative x to the third. So if you graphed that, this side would go up, this side would go down. So we would say as x goes to infinity, what's happening with y? And as x goes to negative infinity, what's happening with y? Well, positive infinity this time is going down, so that would be negative infinity. And this side's going up to positive infinity. Notice that they're opposite signs on this, so I always remember that it switches on the odd ones. So looking at this, it says for each graph, describe the end behavior. Is it odd or is it even? And state the number of real zeros. So describe the end behavior. Is it odd or is it even? I can kind of do these out of order maybe. How many more of these do I have? Okay. So first of all, right away, I should be able to tell if it's odd or even because look at the graph. The arrows are going in different directions. So I know that this is odd. I can also state the number of real zeros. Real zeros are x-intercepts. So that would be right here. So there's only one. And then the hardest part is being able to write out the end behavior, okay? So I really do want you to do this. As x goes to infinity, what does f of x go to? As x goes to negative infinity, what does f of x go to? Practice doing that, okay? And on this one, the right side, what's happening? Well, it's going up, so it's going to go to infinity. This side's going down, so it's going to go to negative infinity. So I know that the leading coefficient is positive on that. What about this one? This one's also odd. That's part B. How many zeros are there? 1, 2, 3. And again, I think this one's going to be the same, right? I should have given you a different one. So this one's going to be as x goes to infinity, f of x is also going to infinity because the right side's going up. And as x goes to negative infinity, as x gets smaller, the left side is also going down, so negative infinity. And then it says to analyzing graphs of polynomial functions. So graph a polynomial function, figure out the end behavior, find the zeros if possible, make a table of values, and then graph points and check the end behavior. And so I have one example here to kind of show you that we can do here. So right away, look at this graph. This is even. It's a positive leading coefficient. The number in front of the biggest exponent is positive. So I know even, both arrows are going to point up. Find the zeros if possible, which means if you can factor this, which I think on this one I could factor out an x squared. The zeros are the x-intercepts. I could get x squared minus 4x plus 3. And then I think I could factor that again and get x and x, 3 and 1, minus and minus. So I'm going to get x equals 0, x equals 3, and x equals 1. So just based on that, I kind of know a lot of stuff about this graph. So I know it crosses the x-axis at 0. I know it crosses the x-axis at 1, and I know it crosses at 3. I also know that both arrows point up, which means it's never going to cross again. So I know this side has to go up and this side has to go up. I just got to figure out what's happening in between. So that's what I mean by make a table of values. Look, don't just pick random points. Find your zeros first. So like I think I would pick 2 on this. And if I plugged 2 into here, which you can totally use a calculator. Let me see if I can get a calculator. Calculators are cool. Get out of here. It's 4 times 2 to the third.
4 times 2 to the third.
2 squared. I get -4. So when I plug in +2, I got -4. So that means from here, I can see that this is going to come down like this, and it's going to go up like this. And I also kind of need to see what's happening between 0 and 1. So not super pretty to do, but I'm going to go ahead and pick 1/2. And I'm just going to plug that in my calculator. -4 times 0.5 to the third plus 3 times 0.5 squared. And I get a really small number, okay? I get 0.3125, which means that this is really like barely coming up. But it's going to barely come up, and it's going to go like this at 0. I'm going to kind of redraw this a little bit. It's going to come like this and go. Something to notice on this, and maybe we'll talk about this more later. Notice that this was x squared, and at x squared, it just touched the x-axis and went back through there. That's not a coincidence. If you have a 0 that has a power on it like that, that's even, it's going to touch the graph and come back down. But these two that don't have an exponent on it, they just cross it through there. So that's a quick way to sketch using end behavior and zeros. Okay, that's it.